My official Arcos project is the MSP 430 tutorial thing that I've talked about a bunch of times. So I'm not really going to talk much about that, and not a lot of progress has been made on that particularly this semester, other than the pilot project, which I will talk about. So for the most part, I focused on working on the programmable intelligent LED board this semester, and on Corsair, which I had talked about for the first time last presentation. So my Kickstarter was successfully funded, so that means the next step is to actually finish up the second round of prototype boards, and then actually start making them. That's all going to happen before February. And as part of that, there's going to be substantial documentation, code samples, and some sort of video tutorials on how to use it. So Corsair has changed a little bit since last time. Of course, it really wasn't much last time. Now it's rewritten in Node.js. Previously, it had been based off of Freenet, which is a great piece of software until you try to edit it and work with it. It's over 200 megabytes of Java code, and it uses some funky UDP multicast packet stuff that RPI's network really does not like. So rather than trying to completely rebuild all of the networking functionality in that, I decided to rebuild the entire thing from scratch and work with a much smaller code base. So I don't have all the unnecessary features of Freenet. Freenet supports things like a forum, live chat, stuff that I would never actually need in Corsair. So now it's written in Node.js, and it basically acts as a backend that generates static HTML pages that you can browse locally on your computer. So anonymous peer-to-peer stuff is apparently a big deal. There's a lot of different anonymous peer-to-peer networks in existence based off many different pieces of software. Generally, some sort of distributed hash table is used for locating a file on the network, but that's not always the best way. So a distributed hash table is basically a way of mapping a piece of data through a hash function to a key, and then saying that key should go on a certain node based on, or that data should go on a certain node based on that key. So it allows you to predict what node will have the data you're looking for, which is useful when you have a lot of nodes storing one large contiguous chunk of data where a part of the data is on each node. So to find a file in a distributed storage system, you can have several major options. You can have a central server. It's really bad if you want to be anonymous. Other than that, it's actually pretty good. Napster had a central server. That was part of the reason why it was so easy for Napster to get pursued legally. You can do flooding like Gnutella does, which is basically like a brute force lookup, where you either send multicast queries out to all the nodes, or you pass it to one node, which then passes it to random nodes until it finds the file it needs. It's reliable and very tolerant of transient nodes, which are nodes that are dropping in and out of the network. However, is very inefficient for large networks. The good things about it are that it guarantees the file will be found if it's on any node of the network. Then you can use a distributed hash table like Freenet uses, which is efficient and results in routes with fewer hops than a flooding method. However, it doesn't necessarily guarantee the file will be found, and if there are lots of transient nodes that are moving in and out of the network, it results in a lot of computation for the network healing, the process of adding those nodes back into the network and calculating hashes for files on those nodes. So distributed hash tables have a lot of difficulty when nodes leave the network without announcing that they're leaving first. Many existing DHT implementations use a circular key space, and if the location it's trying to store it to is no longer available, it stores it on the next available spot. And a lot of peer-to-peer file storage uses that sort of implementation. However, obviously, data can become unavailable if all the nodes that have redundant copies of it are out of the network at a given time. And you can obviously easily calculate or predict which nodes have the data you're looking for, which is kind of the point of a distributed hash table. However, if you're trying to maintain anonymity, that does not work out too well. So you have to work a bit beyond just using a distributed hash table. Yeah.
Isn't it true for all networks that the data can become unavailable?
Yes, it is.
I was making sure that's not a DHT.
Yeah, but that's especially in a distributed hash table system. If you have a key pointing to a few nodes, you know that the file's most likely going to be only on those nodes. So you're less likely to have redundant copies floating around the network in other places. And for example, Freenet works so that related files will be stored in physically similar locations due to the way the hash function works. So if you were to have a section of the network drop out, like let's say a campus where there was a lot of academic papers being hosted from a lot of people using Freenet, if all the internet for that campus were to drop out, all of the academic related papers would likely drop out due to the way Freenet's hash function maps similar subjects to similar IPs, so that you have fewer hops between them for getting multiple parts of a file. So if you had a chunk of a network drop out, you're more likely to lose all of the files relating to something rather than just one chunk of one file drop. Which could be a problem, could not be. It depends. I mean, it works pretty well for Freenet. Freenet's worldwide and has thousands and thousands of people using it. So Freenet uses a distributed hash table, and it encrypts the hash, so on any individual node, you have no idea what's stored in your cache. And that's kind of important since you can no longer be held liable for the files you're hosting, or the fragments of files you're hosting. And Onion routes the requests, so it's hard to tell who's actually requesting a fragment of a file, even though you can tell what is being sent from the node if you're the node operator and you're running some sort of program to track that. Freenet's ultimately designed to operate as a dark net, though, where all nodes are trusted. So for anything like normal use, where you haven't added all your friends' computers to it, and only your friends' computers, it doesn't have the same security. So it's possible for one node to learn the addresses of all other nodes in the network, essentially, if you're running an open net node. So for something like Coursera, where it's designed to be operated as an open net instead of a dark net, where you don't have to manually enter the IP addresses of all the computers that you want in your network, something like this would not work as well. So Coursera uses a flooding-based routing, and it's onion routed, and each node-to-node transaction is encrypted, and at any given point, at any given node, the packets don't reveal the source or destination nodes. Obviously, that's where onion routing is. And in those packets, there's dummy data that matches the size of the data you're expecting. And after it's gone through a set number of hops, or more than a set number of hops, that dummy data will be replaced with real data and then sent back to you. So at any given point, if you're monitoring the network from not within a node, you'll have no idea if the data is real data or if it's dummy data. So at each transaction, this is between a node and an adjacent node that it's communicating with within a route. There'll be a file with a known hash value that you're requesting by node A. There's some counter that's associated with the hash, and it starts at a constant that's going to be greater than 1. That's the number of hops that it has to take before it can be returned. So the request is sent to node B, which has the file. So node A requests a public key from B. B sends it the public key. A encrypts the query hash, the random data, and then sends that to B. B decreases the counter value after it's decrypted it, and then checks if it has the file. If the counter is less than or equal to 0, it replaces the random data with the file and then initiates a transaction in reverse direction. If not, it initiates the same transaction again with another adjacent node to B. So in a small network, this is not too bad. It will result in a lot of transactions, but that's okay. In fact, that improves the anonymous aspect of it, since it makes it harder to tell where it's originating and where it's going to. The only slight problem with this, and this is something that peer-to-peer networks always run into issues with, if a node in the middle of the transaction chain drops out and then it tries to return a packet back along the same chain. If that happens, that chain is no longer valid, the packet has to be thrown out. You can't recover from it because no nodes know anything other than their immediate neighbors. So the networking backend is mostly functional at this point. The encryption isn't in place, however, that's not a major change. I'm not going to be writing that from scratch. And there's some basic templates for the front end, which I'll show you now. These are generated by Node.js, written into HTML and CSS files on your hard drive. And then you can browse those whenever. You don't actually need to be connected to the internet to use the files you've already downloaded. So this is what it looks like right now. It's pretty simple. It's supposed to be pretty simple. It doesn't have anything dynamic on it. Nothing moves around. It has on the side your list of classes, and then when you click on one, it'll take you to a page that would have, or the list of departments, and it'll take you to the page with the list of individual classes that people have added files or documents for. And then when you click one of those, it would take you to more information for it. Right now, since I don't have any of this data put into it, there's nothing to go to. In fact, this is about all you can do on it. When you click on these individual classes, you'd be presented with another list just like this with all of the things that have been uploaded for it in the same way, in sort of like a hierarchy, where you can have folders and files within those folders. And then documents, when you open one, will open in this spot here. And you can view it in the browser, or you can download it out of it, or view it in some other program. So that's what I have for you today. Thanks. Have a great Thanksgiving.
Or break.
Or break.
I like that.
How about the back end? You showed the front end.
Yeah, I don't have a back end running just because I need a handful of nodes running to demonstrate it. I'm hoping to have a beta functional in like the near future, a few weeks maybe. At this point, I've tested it on campus to some extent. It needs minor changes, but it is capable of routing requests and communicating and building a peer table for each.
So could this be part of the study group thing?
Well, the idea is that this would be used for educational materials, so people write notes in class, they could then upload them to this, and they would be distributed around peer-to-peer. Yeah.
So when you're doing your underrouting, each node knows what data is being requested.
Theoretically, yeah.
Right, because from what I understand from like onion routing and Tor,
Normally you'd end-to-end encrypt it as well as peer-to-peer. However, in this case, it doesn't really matter since it's all public data, public within the network. So anyone could request the same data anyway. It's not for secure communication, it's for anonymous communication. You could do end-to-end encryption with essentially no change to the way it works. You just need one more transaction down the chain first to get a public-private key across from the node where it's coming from to. But since it's all data that anyone could access anyway, I don't see any real need for that. It wouldn't improve any anonymous aspects of it, since the data is not supposed to be private.
So what's the need for anonymity in this network?
Not any real major reasons other than it could be used for something other than files at RPM.
So we're not any of those things here. Okay. Jenny, do you have any?
yeah, I do.
Okay. Okay. So Jenny is the last speaker.